All right. Well, it is my extreme pleasure to introduce our speaker today. It's Dr. Linda Cremonesi. She got her PhD in 2015 from Queen Mary University. And she did a measurement on pion production on resonant pion production on water in the TDK experiment. Following that, she postdoced at UCL, where she worked on the ANITA experiment and NOVA and DUNE with a focus on neutrino interactions and neutrino oscillations. She has recently joined Queen Mary University of London again in 2020 as a UKRI Future Leaders Fellow. And she is a colleague of mine. She co-convenes the NOVA Near Detector Working Group and DUNE Near Detector Software Integration groups with me. So she has to put up with me on a frequent basis with lots of frequent Zoom meetings. And I couldn't be more pleased to have her here to tell us about recent results on neutrino interactions from the NOVA experiment. So Linda, please take it away.
Thank you, Matt. Thank you for this lovely introduction and for inviting me to give a seminar. You should hopefully see my slides.
Looks good.
Fantastic. So today I'll talk to you about the secrets of neutrino interactions in the NOVA experiment. So first up, hi everyone. It would have been better to meet you all in person, but one of these one of the good things of these virtual meetings is that we can I can get to give a seminar to a place on the other side of the ocean. So since you can't see me in person, I'll just put here some pictures of me doing physics in a few places around the world. So what we're going to do today is if we go to that, okay. What we're going to do today is the outline of this talk is that I'll first introduce neutrinos, then I'll talk about the NOVA experiment, and then I'll talk about the two analyses that I'll present today. So the NuMI CC inclusive and the NuMI CC inclusive measurement. And don't worry if you've no idea what CC inclusive means. We'll get to it during the seminar. And then finally we'll look at the future. So first up, neutrinos. So you may note that the section of this talks are divided into different songs that probably tell you how old I am, because that's inevitable. So first up, let's start thinking about neutrinos. So what do we know about neutrinos? We know that neutrinos have an extremely small mass. At most, their mass is 1 million times smaller than that of an electron. So that's pretty small. We also know that they're very abundant. So when we do outreach talks, I don't know how many of you have done outreach talks before, but the classic thing is asking your audience to stick the thumb out and look every second. There's 65 billion neutrinos going through your thumb, and those are just the neutrinos coming from the sun and so on. So they're very abundant. They're everywhere. And you have billions going through your thumbnail every second, going through trillions, going through your body every second. But then the other fact that we know about neutrinos is that they only interact via the weak force. So if you think out of all of these trillions of neutrinos going through your body, you can make a calculation and just assume some energy, assume an interaction cross-section, and then you find out that on average, in your lifetime, you'll only interact with one neutrino. So trillions and trillions through your body every second, but on average in your lifetime, you will interact only with one of them. And then the fourth thing we know about neutrinos is that they change flavor when they propagate. And this is a pretty cool fact, actually. And so let's see what that means. So neutrinos come in three flavor. And then we talk about a neutrino flavor with the the charged lepton that we associate the neutrino production or detection with. So in this case, I have an example in which we have an electron neutrino that is interacting with our material and then produce an electron. So we'll call this neutrino an electron neutrino because it produced an electron. And this is why and how we sort of distinguish the three flavors, depending on which charged lepton they're associated with. So we have electron neutrinos, we have muon neutrinos, we have tau neutrinos. And in 2015, well, it's been a few years, but in 2015, the Nobel Prize in Physics went actually to the discovery of neutrino oscillations, which is the phenomenon for which neutrinos can change flavor when they propagate from a place to another. Neutrinos that are produced in a flavor can propagate and oscillate into a different flavor, and then go back into the original flavor, go to the third flavor, and so on. And this is the phenomenon that is called neutrino oscillations. But what does this have to do with neutrino interactions? The title of this seminar is related to neutrino interactions. So let's see how these are related. Actually, I take it back. Let's see before that. Let's see some big questions that you can look at with neutrino oscillations. So the first big question that we can look at is how much actually these neutrinos mix with each other. So we know that these flavors mix quite a bit, but there is in particular two flavors, the muon and tau neutrino flavor, that we know mix with the third eigenstates, but we don't know exactly how much. And if they mix exactly the same way, it could be an additional symmetry. And again, in physics, whenever there's a symmetry, we get all really excited. Another thing that we can look into is the neutrino flavors, neutrino oscillations happen because the neutrino mass eigenstates are not the same as the neutrino flavor eigenstates. So we have three neutrino masses, but we don't know which one is the lightest. And knowing which is the lightest neutrinos can give us very interesting information. So it can be linked to ground unified theories, or it can also give us some additional insights of the nature of neutrinos, on whether neutrinos are Majorana particles, so their own antiparticle. And then finally, with neutrino oscillations, you can also check if neutrinos and antineutrinos oscillate in the same way. And finding differences there will be another Nobel Prize. Another Nobel Prize worthy discovery. I can't promise you a Nobel Prize, but I think it will be a Nobel Prize worthy discovery, because you can link the differences. If we find differences in the neutrino and antineutrino oscillations, then we can link that to the matter-antimatter asymmetry in the universe. So if we can take a step back 14 billion years ago, the Big Bang, after the Big Bang, we had an equal amount of matter and antimatter. But now we fast forward to nowadays, and we look around in the universe, and all we see is just matter everywhere. And so the big question is, where did all the antimatter go? So one possible hint, it would be through these differences in neutrinos and antineutrinos oscillations. So far I told you why neutrinos oscillations are interesting, but how are they connected to neutrino interactions? So if we want to measure neutrino oscillations, we need to predict and know how many oscillated neutrinos we find at our far detector. And this number actually depends on quite a few factors. So first up, it depends on how many neutrinos we actually generated. So how many neutrinos we produced in our experiment. So the first dependency is on your neutrino flux, so the neutrino that you actually produce. Then if you want to see a neutrino, that neutrino needs to interact. So if you remember one of my first slides, I was telling you that neutrinos don't have an electric charge, and so we can only see them when we interact with our material and produce other particles, like in this example right here, in which these cells are detected in a detector. But then you also need to reconstruct these. So to the dots and pixels that you can see in this image, you need to try to say this was a proton and this was a muon. So you need to understand your detector response. And then finally, you need to understand the oscillation, the neutrino oscillation probability. So what I'll focus on today are these measurements of neutrino interactions, and this is how they fit into the big picture of neutrino oscillations. So let's move on to the NOVA experiment. And so for the NOVA experiment, I chose a picture that I think was actually taken at our collaboration meeting. I don't remember what year it was. Was it 2018, in which we were right there in Wichita? And you can probably recognize a familiar face right here at the front. I'm more in the middle of the crowd with different hair because it was a different time. So the NOVA collaboration is composed of 260 scientists and engineers from 49 institutions and in 8 countries. So what does NOVA do? NOVA is a long baseline neutrino experiment, which what it means is that we produce neutrinos at Fermilab, all in the same flavor, all mu neutrinos, and then we throw them to Minnesota. And that's 810 kilometers. If you want to know how many miles is that, that's 500 miles. And for the Proclaimers fan, for the fans of the Proclaimers, that's the link to the song for this section. Anyway, so they travel these 500 miles, and in these 500 miles, they oscillate from a beam composed all of mu neutrinos to some of the other flavors that appear as well. But our flux at the near detector can be used to calculate these cross sections to analyze the neutrino interactions, and so this provides a rich data set that we can use for these sort of measurements. And our near detector is located 1 kilometer from the production target of the beam. So first up, how do we actually make these neutrinos? And this may look like a bit of a complicated diagram. So let's start from the beginning, which is the left. So we make neutrinos by taking protons, we accelerate protons, and then we impinge them on a target. You might not see very well, but right here, there is a thin target that is made of graphite. And you need to imagine, so graphite is the same material you've got in your pencil, and you need to imagine something that is like 2 meters long, and that's roughly the size of our target. So we impinge our protons on the target, and in this produce some particles that are pions and kaons. The pions and kaons are then focused by our 2 horns. And for neutrino mode, we keep positive pions. So we focus positive pions. And then in the decay pipe, which is a pipe that is almost 700 meters long, the pions and kaons decay into muons and mu neutrinos. And then all of the stuff that is afterwards, after the decay pipe, that's mainly concrete to absorb the muons and absorb the hadrons that are produced. And of course, we have muon monitors and hadron monitors to actually monitor these particles. But in this way, the mu neutrinos are produced, and they travel then from Fermilab onwards. The beam that we use is called NuMI. NuMI is stands for neutrinos from the main injector. And what you can see here in this plot is the performance of NuMI over the past few years. So each of the dot is the daily exposure in POT, that stands for protons on target. That's literally the amount of protons that got thrown on the target every day. And that was what each of these dot means. And you can see that the units is 10 to the 18. So that's the amount of protons that we actually throw on the target each day. And then on the right-hand side, so the lines, those are the cumulative exposure. So that's if you sum them up, integrate them through time. The orange times is when we were running in neutrino mode, and the blue times is when we were running in anti-neutrino mode. For the analysis that I'm going to show today, we are using this fraction of our neutrino data, which is about 8 times 10 to the 12, 10 to the 20 protons on target, but were collected at the near detector. So I told you how to produce neutrinos. I told you how many neutrinos, or how many protons of target we collected. Now, how do we detect the neutrinos? So we detect them with our NOVA detectors, and we use the NIR detector for this analysis. The NIR detector is made of, so you can see it right here on the left. The beam is coming from this sort of blue direction. You can see a person here for size comparison. And it's made of these extruded plastic cells. So you can see the plastic cells right here, and these are filled with liquid scintillator. So what that means that in each of the cell, when a particle goes through the cell, it emits scintillation light through the liquid scintillator, and then the photons are collected by this fiber, wavelength shifting fiber, that then brings it to our electronics, basically. And if you want to see how basically this looks like, so each of these cells will become a sort of pixel in this diagram right here in the top right. And so this is a view from the top of our NIR detector. So if we were looking from above here, and it's made of mainly hydrocarbon and chlorine and a little bit of titanium dioxide. So downstream, at the downstream end, so right here at the bottom, and here you can see in the diagram, we have a muon catcher, which is made of these NOVA cells, but with some steel in the middle. And the reason is because we can then range out and sort of catch the muons that have of 2 GeV and above. So at the NIR detector, we see a flux of neutrinos that we produced in NuMI, and this flux in neutrino mode is 95% pure in muon neutrinos. So this is a spectrum, and on the x-axis you see the neutrino energy, and then basically the flux on the y-axis, and it's a log scale. So you can see how many more muon neutrinos we get of than the other flavors. Then we have a little bit of muon antineutrinos, and then our electron neutrinos are about 1%, and you can see them right here in blue. So what type of interactions do we see at the NIR detectors, and what type of interactions we're measuring in these analyses? So these interactions are called the charge current, and they're called the charge current because there is a W boson exchange in which from the neutrino we have the production of a charge lepton, which tells us the neutrino flavor. And so charge current inclusive analysis will look at all the possible charge current interactions that happen in our detector. So some examples that you can see here are a quasi-elastic interaction in which the neutrino interacts with the nucleon, and then a charge lepton is produced, and then a different nucleon is produced, but nothing else. Then we have a resonant interaction in which we have a very similar sort of process, but through a resonant production, we also have a pion that is produced, or a deep inelastic scattering in which lots of pions are produced. And on the left, you can see a summary of how some of these processes have been measured by other experiments in the sort of NOVA range. And you can see there's a lot of data points, but they're not very precise. They're, sort of like going up and down. And the other thing that is important is that we don't really see great agreement right here. So far, I gave you a very simplistic overview of how neutrino interactions work, but what's actually happening is that these interactions happen in the nuclear medium. And so we have nuclear effects to account for as well. And so a nuclear effect that only became apparent in the past few years is meson exchange currents. And this is an interaction in which the neutrino interacts with two nucleons at the same time, and then produce basically a different pair of nucleons. But additionally, other nuclear interactions are because the neutrino interactions happens inside the nuclear media. And so here we have an example of, for example, a proton being produced, but then, interacting with a proton, and then a charged pion being produced. But then this charged pion needs to sort of travel through the nuclear media. And so other stuff happens. It can happen pion production, absorption, elastic scattering, charge exchange. So all of these is happening while so you have your neutrino interaction, which is these cartoons that I showed on the right. But then on top of that, the products need to travel through the nuclear media, and other things happen, which make the interaction a lot more difficult to understand from a detector point of view. So I talked to you about interactions, and I also talked about cross-sections, but how do we measure a cross-section? What's a cross-section? So a cross-section is a measure of how likely, if you want, is an interaction. And the way we measure it is that we take the number of events in our selection, and then we correct that with a purity. So we find how pure is the sample through an estimation from our simulation. And then we divide that by the number of targets. So the number of targets is the number of nucleons that your neutrino interacted with. And so you can calculate that based on the geometry of your detector, and you know what material it is, and so on. And then you need to divide by the flux. So you need to know how many neutrinos you produced and how many neutrinos went through your detector. And finally, you need to correct for the efficiency, because of course you're not 100% efficient. So you'll miss many of the neutrino interactions because of difficulty in detection and acceptance and other effects like that. So I now give you an overview of neutrino interactions and neutrino cross-sections, and let's see them in the context of NOVA. So I talked about neutrino flavors, and so these are an example of interactions that we have at the NOVA near detector. So in this case, in the top case, for example, we have a mu neutrino interaction, and we know it's a mu neutrino because the track that is produced is very long and it's fairly straight. And so this long straight track is a sign of a muon, and so we know that will be a muon neutrino. Similarly, for an electron neutrino, we have the production of an electron, and we know that it's an electron when we have a short, sort of wider fuzzy shower that comes from the electromagnetic interaction in our detector. And then finally, a neutral current interaction is an interaction in which we don't have a charged lepton that is produced, so we don't have an electron that is produced or a muon that is produced. And what we would see is something like a diffuse activity from the recoil of the system. So hopefully I now give you an idea of what we can do with the NOVA near detector. And now I'm going to present to you the two analyses that I'll talk about today, which are the NuMI CC inclusive and the NuMI CC inclusive analysis. So the NuMI CC inclusive analysis are so as you remember from the beginning, you may remember, I don't know, our beam is 95% pure in muon neutrinos. So we have a very high number of these interactions. So what's the first step in this selection? So here you can see an event display of our near detector. The top panel shows the top view, so it's as if you're looking at the detector from the top. And then the bottom panel also shows the side view, so as if you're looking at the detector from the side. The beam is coming from the left, and each of these pixels corresponds to a little bit like one of those cells that I showed you earlier. So first up is that we associate all of the hits that come more or less, that are spatially close but also temporally close, that come more or less at the same time, and we put together in tracks and showers. And so you can see them, that some of these tracks have the same color because they are they belong to the sort of like the same event, like this green event right here is the same color as this green event right here, because we correspond to this two views of the same event. So we call a vertex the start of the track. So this will be the vertex of a specific interaction. And so the first step is to require the vertex to be inside this solid volume and the whole event to be inside the dashed volume. So we want the event to be very well contained, because then we can measure the energy, we can measure the property quite well. And we want the vertex to be inside this smaller fiducial volume, because again, we want to be able to measure the property of this event quite well. So what's the second step then? The second step of the analysis is then to try to select these muon neutrinos. So to try to select the muon neutrinos, so distinguishing them from other interactions and mainly neutral current interactions, then we need to look at likelihoods. So we know what the signature of a muon looks like in our detector, and we know what the signature of a pion looks like in our detector. So we make distributions of the energy deposited that a muon or a pion would leave in our detector, and compare them to the to what we have for our tracks. And so we do something similar for the scattering, and then look at the average energy deposited as well from these tracks. So we can use these 4 variables and input them in a boosted decision tree. And then from the boosted decision tree, we can get this distribution of what our muon ID variable. And you can see, so in blue, we have the true signal, and then in red, we have neutral current, which is our main background, and then we have a little bit of electron neutrinos in green. So with these 4 variables, we produce a BDT in which is very peaked at 1 for the signal and very peaked at -1 for the background. So we put a cut at roughly 0.25. And we get a sample that is about 86% pure and 90% efficient with respect to the previous cut. So what does our sample look like in terms of like the interactions that I was talking about earlier? So these 2-dimensional plots have the cosine of the angle with respect to the beam direction on the x-axis, and on the y-axis, that's the muon momentum. And then these are divided into the 4 interactions I was talking about earlier. And again, these are all part of our signal. And you can notice that we have sort of like different regions that populate our 2-dimensional space of the measurement, depending on the interactions. So QE, quasi-elastic, and MEC are very forward-going and slightly higher in energy. Resonant sort of spans these, I don't know how to say it, like sort of diagonal bit of space, whereas the deep inelastic scattering in the case of course of our measurement is in this sort of like higher angle region. So the measurement itself is performed with a similar formula to what I showed you earlier. So if you can retrace each of these terms to the rainbow formula I showed you a few slides ago. But you may notice that there are some subtle differences. And one of the differences is these addition of these bins in the muon kinematics. And this is because we're performing a double differential cross-section. So our cross-section depends, it's calculated in each bin of this 2-dimensional space. So here on the right, you can see again the space of the reconstructive cosine of the angle and the reconstructed muon momentum, which is the space in which we make the measurement. And this is a flux average differential cross-section in 172 bins. But you may notice, that in this formula, there are also an additional factor that I call the E-avail. It's the available energy, which is the total energy of the observable, of all observable final state hadrons of the system. And we don't report on it. We use it to calculate this purity correction and this efficiency correction. But then we integrate over it and report the cross-section just in the 2-dimensional space. So you're probably wondering why you're doing this. You know, it's not something you're reporting. So why are you correcting the purity and the efficiency in this third dimension? And the reason is because we can see a dependence of this efficiency purity on this third dimension. And this is yet again, this is a different type of plots from the ones I showed earlier. So all of these panels show distributions of the mu momentum, but each of the panel is in a different bin of cosine of the angle. And from the top left, that's the most the highest angle, and then we move to the right and we go more forward, 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 forward until the most forward bin is on the bottom right. And there's a lot of information here that you know, you might not be interested in it. So the bottom line here is that the efficiency is not the same in the different bins of available energy. So at low available energy, that's the red line, and then medium is the other two lines, and then high available energy is this like sort of dashed and dotted blue line. So you can see the lines are not on top of each other, and that's what matters here. And that's the reason why we do the correction in 3 dimension. And then similarly for the purity, and these are very similar plots to what I showed earlier. And all you need to care about is that these lines don't sit on top of each other, which is why we perform these corrections in 3 dimension. So we now have a NuMI CC inclusive sample, and these are just example of event displays for these events. And you can see that what they all have in common in this very long straight muon track, and they all have it. Some have, you know, a little bit of activity, some have some other tracks, some are just one long track, but you know, it doesn't really matter. This is a CC inclusive measurement, so these are all part of a signal. The important thing is that we have that long muon track. And after our selection, we have more than 1 million events. So this is a huge amount of neutrinos. In neutrinos, we're not used to these numbers. Like, you know, we're used to hundreds, sometimes thousands. So actually having 1 million events after your selection is pretty good. Of course, we have a way to evaluate our uncertainty, which is we account for uncertainties with covariance matrices, but the bottom line of all of this is that the typical uncertainty is about 12%, and most of it actually comes from our flux. So the uncertainty on the neutrinos that we actually produce, which is an uncertainty of around 10%, and it's a normalization uncertainty. We have plans to reduce this uncertainty with some additional measurements that I'll talk about later on. So if we want to see, this is the measurement, all 172 bins, again, divided into panels. Each of the panel contains a different slice of cos theta that you can see right here at the top. And then in each panel, we have the x-axis that spans the muon momentum. So here, the y-axis is your double differential cross-section, and it's compared to the neutrino event generator that we use. So these are two slightly different versions of the neutrino generator, and the solid line is for when we use a tune that was developed by us, and then the dashed line and when we use the neutrino event generator out of the box. And it's a little bit difficult to pick out different sort of like behaviors in different slices when we have so many in front of us. So I just chose 4 slices, and I'm going to look at them into a little bit more of details. So these are the same plots as we were in the previous slide, only just sort of blown up slightly bigger. So we can see in all of these that we have good agreement between between our measurement and the generator in the higher sort of like higher angle slices. But in this very forward slice, there's a clear sort of like disagreement between, so we agree quite well with the tune generator, but the dashed line is quite a bit above where we are. And if you remember from my 2-dimensional plot, what did this area correspond to? That corresponded to the area in which we have the most of quasi-elastic and meson exchange current events. We can also compare this, our measurement to other neutrino generator, and these are listed right here on the right. We have GBU in cyan, we have Newt in green, and we have Neuro in purple. And these are out-of-the-box generators. These generators haven't been tuned to our data set, and we can see that they already produce quite well the shape of the data. And there is we notice that in particular GBU sees an overall sort of normalization difference, but when we repeat this exercise with shape-only distributions, we can see that then GBU performs similarly to other generators. Oh, sorry. Now let's look at the electron-neutrino measurement, and this measurement comes from about 1% of our flux. So this is a plot that I showed you earlier on, which is the neutrino flux at the NuMI detector. And so you can see that it is 95% pure in mu neutrinos. But if we want to look at electron neutrinos, those are the ones coming in this blue line, and that's about 1% of our beam. So that's quite a small amount that we can see that we have right there. So that makes the analysis a lot more challenging. Because it's a lot more challenging, then we developed a machine learning algorithm to better classify and select these events. So we identify electrons using a single particle identification, which is done with a deep convolutional neural network. And the neural network is trained on single particle. So the single particle that are simulated within the detector. But then what we do in our reconstruction is then we divide the interaction we separate it basically using some geometric reconstruction methods. And here is an example in which we'll have a first cluster, a second cluster, and a third cluster. And what the network does is that it looks at 2D views of the deposited energy of the single particle. So if you remember the event displays that I showed you earlier, not something like that, but something similar. So instead of having the event display, you will have similar views of, but on the z-axis, there will be the energy deposited. And each reconstructed particle is then classified as electron, muon, pion, photon, and proton. So this is single particle. Deep neural network is used as one of the inputs to our classifier, because the second important part that we need to select these electron-neutrino interactions is to provide context. And so to do that, we use a boosted decision tree in which we use the output of the deep convolutional neural network and then add context. So add information about the width of the shower and the gap to the vertex. So when we have the particle only, we only have information about this shower, like the case on the left. Whereas if we add information about the full interaction, so we have information about the width and the gap, then it becomes easier to distinguish these electron-neutrino interactions. So when we put all of this together, we get a distribution of the electron ID that you can see right here on the right. And you probably just noticed straight away that it's not as peaked as sharply peaked at 1 and -1 like the muon ID was. And this is, of course, because this is a much more challenging sample. Our signal in this case is the blue histogram. And then the two main backgrounds are NuMu in red and neutral current in pink. The strategy of the analysis then has to be different because there's not really a clear place where to put a cut where you can select these events. So the strategy is to make a double differential cross-section in electron-neutrino kinematics. And by the way, this is the first that was ever done because the electron-neutrinos are extremely difficult. So no other experiments had been able to actually select many electron-neutrinos to be able to perform a double differential measurement. So the formula, again, right here is very similar to the rainbow formula that I showed at the beginning. But there is an additional complication in this case in which in each of these bins, we look at the electron ID, so the distribution that was calculated with the boosted diffusion tree, and we perform a template fit. So we fit this distribution using templates of our signal and our background, and we use that to get a handle on our background, to have a measurement of our background in each of these bins. And then we perform a background subtraction. Overall, this measurement has typical uncertainties of about 17%. The flux is, one of the main uncertainties, but there are other uncertainties that play a role here. In this case, calibration and detector response are are some of the main uncertainties, because the electron energy is calculated from calorimetry, and also the interaction modeling part contributes quite a bit to the uncertainty because of the large background. So out of the sample that we had at the beginning, only 1% of our flux, of our event rates, but we still managed to select about 10,000 electron neutrino events. And here you can see an example of them, that the main feature that we all have is this short and wide fuzzy electron shower. So this is the measurement. It's again a two-dimensional, a double differential a double differential cross-section. This time in the electron kinematics. So each of the panel is a different angle, but this time in the electron. On the x-axis of each of these panel, we can see the electron energy. Again, this is compared to our two versions of Gini, in which we see good agreements pretty much everywhere. And then we can perform the same exercise in which we compare it to our generators. Again, in more recent version of Gini, then Jibu, Newt, and Nuro. And we can see pretty good agreement pretty much everywhere in this case. But if you notice, these are like wider bins, and so it's not too surprising that we actually see quite this level of agreement. So let's look at the future. What's in the future for us at NOVA in these in these measurements? So most of NOVA cross-section measurements are limited by the calibration, detector response, and flux uncertainties. So we have a test beam experiment currently running at Fermilab, where we have some NOVA modules, but just put in front of the Fermilab test beam beam. And the aim there is to reduce the calibration and detector response uncertainties. Whereas to reduce the flux uncertainties, we currently have an analysis looking at the neutrino electron cross-section measurement. If you're wondering how will that reduce your flux, your flux uncertainties, that's because the neutrino electron cross-section is very well measured. And so when you measure the event rate, an event rate is just a cross-section times the flux. So if you know the cross-section theoretically very well, then you can get a precise measurement of the flux. I didn't cover a lot of other things, so I only talked about neutrino interactions today. We do quite a lot of other things in NOVA. Quite crucially, I didn't cover our neutrino oscillation analysis that was presented at Neutrino 2020 a few months ago, and I also didn't cover one of our latest results, which is one of the first sterile anti-neutrino searches through neutral current disappearance. So as a summary, I showed you, hopefully got you a little bit excited about neutrino interactions, or as excited as Matt and I are. So I talked to you about our mu neutrino analysis, in which we have more than 1 million events. That's a truly huge sample when we talk about neutrinos. We'll have 172 bins, and with pretty small uncertainties, around 12% typically. And then I presented the first double differential electron neutrino charge current measurement. And again, we got about 10,000 events from a very small amount of the beam, because only 1% of our flux comes from electron neutrinos. We have an active neutrino program that is looking at the ratio of these cross sections as well, and the anti-neutrino version of these analyses will come out soon, as well as more exclusive channels and as I said, data-driven techniques to reduce our uncertainties. So finally, I'm going to leave you with a more recent picture of us, which is from actually last year, our first online collaboration meeting. But since then, we've all been online. Thank you.
Great. Thank you so much for the very excellent presentation, Linda, and also for the great recommendations for my Spotify playlist for the rest of the afternoon. We have plenty of time for questions now. If people want to raise their hands to ask questions, I can call on you. If you feel more comfortable putting your question in the chat, I can also relay that through the chat. So please, any questions about neutrino interactions, these results, how we make neutrinos? So Linda, I'll try to break the ice. Oh, so Tyler's asking a question on chat. We'll go to Tyler first. He's asking what is the liquid scintillator?
Scintillator made of? It's mainly carbon. Let's see. I think I had the composition right at the beginning. Ooh, what is that? Yeah, it's hydrocarbon, which is and chlorine, which is carbon and some hydrogen and some chlorine.
Yeah, it smells like gasoline if you have it like out in the room, basically.
I actually never had the pleasure to yeah, I think yeah, and I never had the pleasure to see it in real life, because I joined Nova once Nova was already running. So
yeah, it's a clear liquid that you know, it's a hydrocarbon, but it's like it's very much a petrol kind of chemical. Like it smells like gasoline because of the pseudocumene mixed with it. I've had the pleasure of basically swimming in it, putting the detectors together. Very, very slippery, but if any light hits it, it emits this like beautiful kind of purple glow to it as well. So it's a pretty cool thing. So we have some more questions coming in. So Tam is asking, can you tell me more about the equation? Tam, which equation are you referring to? Could you clarify that one? Maybe the cross-section equation, this one? Oh, I think he's asking about the very extended one, probably with the unfolding, it looks like.
Yeah, this one.
Yeah.
Yeah, so this is a version of that same equation, of the rainbow equation, but with some additional terms. So if we go in order, the first term at the top in the rainbow equation was something called the number of events. But those are your number of events, they are in your true space. So to do that, you need to follow a procedure that is called unfolding, which is you make an assumption on your distribution in the reconstructed space, which is what you can measure. And then you apply this unfolding matrix that lets you basically transform a spectrum in the reconstructed space into a spectrum in the in the true space, which is then what you can compare to your neutrino event generator, so to your simulation. So that's, if you see these like u to the this matrix u to the -1 ijk, that's the unfolding matrix. The other thing that I should have probably mentioned it earlier. So we can see that the number of selected events here depends on 3 variables. So 2 of the variables are the muon kinematics, which are the variables that are used in our double differential measurement. So here on the left, this is a double differential cross-section measured in bins of cosine of the muon angle and muon momentum. So that's why in each of the parameters depends on those 2 variables, and then there's the additional available energy, which we use to apply the purity correction and efficiency correction as well. And this is because we don't know what's the dependence of the cross-section on the hadronic system that is also produced. So when you have a neutrino interactions, if it's even if it's a quasi-elastic interaction, you have a proton that is produced, and then this proton, of course, goes through the nuclear media, and some other hadrons may be produced. But there is some dependence of your cross section on these on the hadronic part of the products, and this is especially important if some of the other interactions come into play, like the resonant interaction in which a pion is produced, or the deep inelastic scattering in which multiple pions are produced. Oh, and finally, and you probably see the other additional terms are these delta cos theta and delta t mu, which are just the bin widths. So double differential, so for each bin, you need to divide by the bin width. All the other terms are the same as the sort of like rainbow equation. So you still have the number of targets, and this time the number of targets doesn't depend on the binning, and that's why it's just a sort of like a number. And the flux, which is how many neutrinos you produced. And again, this is just a number, so it doesn't depend on the binning. So the dependence on the binning only comes in through the number of events you selected, your correction of the purity, and your efficiency correction. I hope that made sense. Okay,
great. Tyler also had a follow-up about he's back on the liquid scintillator. Now he's curious, oh, maybe Holger's answering, and he's curious what exactly, why do we choose our liquid scintillator? Like, what makes it the material we chose to make our detector out of?
Yeah, so I think, I mean, the various reasons, like, you know, you want a scintillator, so you want a material in which when a charged particle travels through the material, you want to we want it to emit photons that then you can collect in your wavelength shifting fiber. You also want a material that is fairly dense, and you also want a material that is not too expensive, so that you can build a very big detector with. You also want a material that doesn't, you know, that you can sort of build in one big, don't know how to explain it, in one big size without having problems of possible breakages. So the NuMI detector is let's see where I have a picture. The NuMI detector is, oh, there it is. So it's 300 tons. I don't have the dimension here on how big it is, but it's about 6 meters by 6 and then by 14 in length. Whereas the NuMI detector is a lot bigger. We're talking, I think it's 14 by 14 by 60 meters. And so things like size and how you can make a sort of like a good continuous material without breakages and price are all coming to play.
Yeah, I mean, that's with these giant neutrino detectors, we try to build cost-effective detection is always, it's kind of a science versus cost optimization game that you play for these things. And I don't know if anybody's following right now, but like we're building out the dune detectors, and we're closely watching the prices of materials that are skyrocketing because of the pandemic at the moment that could seriously impact the kind of science we might do if those prices stay high. So yeah, you become kind of when you build these large detectors, you somehow start doing weird commodity trade work and becoming like trying to follow these pricing indexes and things. So it's interesting. Like, I don't know if people know, but like the cost of steel and copper right now is like up like a factor of, sort of like, I don't know, like 8 over its historic average or something. It's like hugely up right now. So
yeah, copper is yeah, there's been a few incidents of copper being stolen from railways up here because of yes, how expensive it is at the moment.
okay, good. Are there more questions for Dr. Cremonesi while we have her? Richard.
Yeah, I was wanting to know how the event generator is, what it means for it to be NOVA tuned as opposed to being a blanket out of the box generator.
Right, did I keep that slide in? Let's see if I did. Right, so the version of the generator that we used was, I did, okay, fantastic. So the version of the generator that we used didn't have a particularly good agreement with our data. So there were a few problems with it, and this is there's various reasons why that is. It's simulating neutrinos is not easy, but there was a lack, a complete lack in the generator of the meson exchange current component. And this is because we didn't know that this interaction actually happened until a few years ago, and the few experiments that had made neutrino cross-section measurements weren't making measurements in the energy range that actually had these meson exchange currents. So NOVA was actually one of the first experiments to look at these. So what we do with the generator and with this version of Genie is we need to apply some corrections to suppress a little bit the quasi-elastic and resonant component, increase in the tail the deep inelastic scattering component, and then add completely these meson exchange model, and it's added in sort of like as an effective correction. And if you're wondering, wait a second, why do you do this? Why do you make this correction and then measure a cross section? And the reason is because of these corrections. So we need to apply the purity corrections, and we need to apply the efficiency corrections. So we need to have a model that is at least close enough to our data to be able to do that. And that's why we apply the correction before making the measurement.
Thank you.
All right, great. Are there more questions? Looks like there's another one on the chat. Would NV centers be useful in neutrino detections?
I don't know what NV centers are.
Tyler, what is NV centers? Tyler, you can unmute if you're able to and speak if you'd like. Or maybe you could put a clarification in chat.
Nitrogen's vacancy centers in diamond. I don't think I know enough about nitrogen vacancy centers in diamonds to as a material to know. Sounds expensive, but maybe even not expensive. I've actually used some diamond terminated cathodes for different purposes, but that was on a very small scale. I'm sorry. I don't know enough about these materials to be able to comment.
Okay, great. Well, maybe we'll go for one last call for questions here. I know that it's, I think, 9 p.m. for Linda there, so probably let her get off of Zoom and relax for the evening. Are there any final questions before